Hello physics students. In the last video, we learned how to find the electric field for charged cylinders. Today, we're going to learn how to calculate the voltage or the potential around charged cylinders. I just want to remind you of the concepts as I often do because it's important to know what we're calculating. So you don't have to write this down, but we calculated yesterday the electric field, and remember what the significance of the electric field is that it causes force when charges are around it. So essentially, once we had the electric field in various regions, we could then find the newtons if you put a proton or electron in those regions of space. Today we're going to find the voltage. Remember, there's a couple different definitions for voltage or potential. Voltage is work over charge, and so if you have for a path like a wire a certain voltage, that means that when you let a charge go like an electron, it shoots through that path and comes out with a certain amount of kinetic energy. If that one electron comes out with just a little bit of kinetic energy, then when we do the joules per coulomb for that electron, we might get 1 volt, a small voltage. If an electron goes through that same path and this time goes really fast and comes out with a lot of joules for that coulombs of electron, then we might have a higher voltage like 1,000. So that's what voltage, the joules per coulomb of charges as they pass along the path. And then a related idea is that, and I really should use the symbol delta here, the voltage from one point to another. The delta V is also then the electric field integrated that lies along a particular path from one point to another, saying the same idea like this, because as this equation, because if you've got a lot of kinetic energy, that means you've got a lot of force and therefore a lot of electric field along that path. So now we're going to calculate the voltage, but remember, voltage without the delta is the electric field encountered from an infinite location from the charge to some point as you integrate in. So it's the path is from deep outer space to a point. What's the electric field along that path? What's the thrust electrons get as they moved either from outer space or to outer space along that path? So that's what we're calculating voltage today. So what we're going to do is we're going to, so here's the title for today, Gauss's law, cylindrical symmetry to potential or voltage. We're going to take the example from yesterday's video, the hollow pipe of a certain charge density rho, inner radius 3r, outer radius 4r. And instead of making this a really long video and re-deriving those electric field expressions, I'm going to use yesterday's video again. But you'll be happy to know that I've modified my time machine here. And this time what it does is it's just going to extract the formulas from our lesson yesterday rather than sending us all back in time. So, ready? Here we go. Okay, so that was hopefully a little bit more convenient. There's the formula for the first region outside this pipe. Now let's get the second formula for the electric field inside the charged material. So, ready? Here we go. Okay, there's the second formula. And we need one more formula for the electric field inside the cavity of the pipe. So, here we go. Okay, so there's our final formula. Let me put my little time machine away. So, now we're going to use these formulas. We could have derived them from Gauss's law. They came from Gauss's law, but today we're going to find the voltage for R greater than 4R. So remember, voltage without a delta is the amount of electric field found starting from outer space, integrating inward to a region out here. So the formula we need, if we want to find the electric field for R greater than 4R, we need the voltage. We want to use the electric field formula that applies out there. So we'll begin by saying voltage, the definition, is negative the integral from, and remember the point of the minus sign is because when you go against the electric field, you're going to a higher voltage. When you go with the electric field, you're going to lower voltage to negative. So that's why we need that minus sign. Okay, so we start with the formula in general. Now we're going to plug in the specific formula we're dealing with. I'm going to lump all the constants together. 7 rho r squared, and the 7 rho r squared, 2 epsilon 0. And then what we have is r to the minus 1 dr, which integrates to the natural log, okay? So minus now, because of this minus sign, what we could do is it'll flip log of r minus log of infinity. It'll flip and put the log of infinity first. So I could get rid of the minus sign. And here's a bit of a problem, because log of infinity is also infinity. So this voltage comes out to be an infinite amount. So the reason why is it doesn't make sense to talk about plain voltage for an infinite line of charge. Because remember I said in the last video that the line of charge is not truly infinite. It's just big enough so that the dimensions we are from the line of charge is relatively small compared to the length, and then we could say it's approximately infinite. But if we come from outer space, that line of charge, I don't care if it's stretching from one coast of the United States to the other, thousands of miles. If you go way, way out, you'll start to see that the line of charge is not truly infinite, even if it stretches across the continental United States. So there is no such thing as a true infinitely long line of charge. It would have infinite charge and infinite voltage. So we won't be, for cylindrical symmetry, ever finding voltage V like we did for spheres coming from infinity. But that doesn't mean we can't calculate voltage. The next thing we're going to do is the only other part. As long as we stay relatively close to this pipe, we can still find changes of voltage, because these formulas will still be valid as long as we don't go very far away. So what we're going to do is find the voltage from 7R to the origin. That's the example that we're going to do. Oh, by the way, I didn't give a pause for you to copy this, so in case you haven't already, I'll pause here, give you a chance to copy this down. Okay, so let's move on to part B. Okay. All right. I just realized I probably shouldn't have erased the formulas. I'll have to look back and hopefully I remember them. So here is our cross section of this pipe. Okay. So this is 1, 2, 3, 4R, 7R. Well, it doesn't matter. I'll say we're starting here, the initial, and the final is here. And like here, we integrate electric field, but we're only starting from here, not infinity. So delta V But what you have to realize is there are three regions of all different electric field expressions. So that means we have to break this integral down into three parts. We have to integrate from this point into this with the formula that applies for out here. Maybe I'll call that electric field 1. And then from here, there's a new formula for electric field, so we need to start integrating from here to here with the other formula for electric field. And that formula ends here at R equals 3R. And then on the inside, there's yet another formula for electric field. So this formula right here, we actually have to integrate with three integrals for each of the regions. Expressed mathematically, we could say this, that we start with this. It'll be minus the integral from 7R to 4R of E1 dot dr. Then that integral from 4R to 3R. And then we stop there because that formula stops there, and we continue on integrating the rest of the way from 3R to the origin. Okay. Now, fortunately, this electric field is 0 in here. So this integral is 0. So really, we just have these two to evaluate. So let me plug in what the formulas were. What was it? 7 rho r squared. Oops. All right, so that's the electric field in here. Again, I separated out the R dependence, lumped all the constants together of that formula that I got from yesterday. And then this formula was all right, so this is the next line filled out. I'm going to pause here, give you a chance to copy this down because I might erase as I go along. So copy this down if you need to catch up. Okay, so let's move on. So this, the constants remain 7 rho r squared over 2 epsilon 0. But the dr over r integrates to natural log of r. And the limits from 7r to 4r. And then this integral, the constants remain, rho over 2 epsilon 0. R dr integrates to r squared over 2. And then minus the 9 r squared is a constant, but dr over r integrates to, again, natural log of r. And we have to evaluate from 4r to 3r. Okay, so now we've got to plug in our limits. So log of 4r minus log of 7r. You know what? I believe I'm going to run out of room on this line, so what I'm going to do is just go like this to give me, but that's from up here. And first I'm going to plug in 3r into here. So we have 3r squared over 2. And then I'm going to plug in 4r into this expression, minus 4r squared over 2. And then I'm going to plug in 3r into the natural log. And then 4r into the natural log. So, by the way, essentially the problem is solved. We just have to touch it up a little bit. By integrating, plugging in the limits, that's the bulk of the credit. But there's just a lot of touching up to do here, so let's continue on. So what I'm going to do is distribute this minus sign through here and make that a plus, minus, plus. Okay, so that makes log of 7r minus log of 4r. You can combine two natural logs if there's subtraction by putting these terms inside the log as a fraction. So I have 7 rho r squared over 2 epsilon 0 log of 7r over 4r. Okay. And then this term. So this is going to be, I could also distribute the minus sign to everything here. So I'll make this a plus, minus, plus, plus. Okay, so now what I have here is 16r squared minus 9r squared, which gives us 7r squared over 2. And then over here, I could combine these two natural logs by combining them as a fraction, log of 3r over 4r. Okay? And I'm going to erase this down here to continue on. So 7 rho r squared over 2 epsilon 0 log of 7/4. Distribute this through. 7 rho r squared over 4 epsilon 0. And then this 9 rho r squared over 2 epsilon 0 log of 3/4. Okay, so maybe I'll stop there. I don't think I could really do too much more. So there's my delta V. All right. So let me pause, give you a chance to copy down all these details. Okay, so it's important, in my opinion, to look at the big picture here because there's so many details and you don't want to get fixated on these details, okay? Basically, the important thing is, one, for cylindrical symmetry, we do not find the voltage integrating from infinity in because it gives us an infinite value, because no cylinder can truly be infinitely long. Then we can find delta V for close displacements where the finite length of the cylinder is still not apparent. So what we have to do in a case like this, starting from one point to another, is we might have to break the integral up into several pieces, integrating in for one electric field expression, integrate the next electric field expression, and then integrate the final electric field expression. So that is something that you definitely need to know, because most of the credit, or a good portion of the credit, would be just maybe the second line here, breaking the integral up into pieces. When you understand that, the AP already gives you a bunch of credit. Okay, and then obviously performing the integral. The important thing, as long as you get something algebraically equivalent, don't focus on all these details. They're not important. The big idea, breaking the integral down into pieces and then performing those integrals for the right limits. That's the idea, delta V from one point to another for cylindrical symmetry. All right, so we'll stop there for today. Hopefully you enjoyed this nice integral, this proof of delta V, and the time, my new little time trick. So I'll see you in the next video, Gauss's law video next time. All right.